Hello and welcome back to Calculus 1. We are starting chapter 3 on derivatives, and the first lecture is going to be on definition of the derivative and the meaning of the derivative and the need for the derivative. Then the rest of the chapter 3 is going to be on ways to take derivatives, and then chapter 4, application of the derivatives. Then we will move on to chapter 5, which is integration, and you will have 2 additional chapters on integration in Calc 2. So we already talked about calculus being a study of change, and derivative is going to measure the rate of change. So the word rate hints to some kind of division already, because we know that ratios and rates are all fractions. So when we think about these concepts, we are going to find again motion and evolution, right? The change in time inside the concept today. So let's start first with this, with the graph, and go all the way from algebra into calculus. So technically, we're going to review a lot of stuff today. So let's have function f of x, and we are going to define 2 points over here, P and Q. And what I'm going to do in blue is draw a secant line. Secant line is the line that cuts through the graph. It's actually in Greek means to cut, secant. So the blue line is the secant line, and the slope of that secant line is y2 minus y1 over x2 minus x1. This is basic algebra stuff that you know for what, 10 years now? Whatever, give or take, right? And then we also have the idea from pre-calculus that y is equal to f of x, where y is the output value from the input x. So now I can actually get this m secant as f of x2 minus f of x1 over x2 minus x1. This is just rewriting the same formula from before. I haven't done anything special to it, right? I just added everything to be in terms of x. So now we see that if we have x1 and x2, and in our case we do have x1 and x2, right? We can deal with this thing. Now what I'm going to do is I'm going to make the point P fixed point, and that fixed point is at a f of a, right? So what I've done here is I created a fixed point P. What I'm going to do next is I'm going to let Q travel. So Q in time is going to start to move along the black line, right, the function line, creating infinitely many secant lines, and each one of those secant lines has a slope m secant, which we can calculate by simply observing the location of point Q. So as it moves, it will swipe through all possible points along the function, and we have point P fixed. So it is, if I rewrite m secant now, so what I'm going to do is I'm going to now call point Q x, and its y value f of x, because it evolves in time, it changes. So as you can see, now m secant, let me use blue again because color code is over here. So m secant now is going to be redefined as f of x minus f of a divided by x minus a. I haven't done much again, I'm just renaming things. So we started with y2 minus y1 over x2 minus x1, then we renamed that into f of x minus f of x1, right? And now I am just, instead of using x1 and x2, I'm using a and x, and I'm just renaming it again. So it's renamed stuff twice already. Now, I can calculate every single slope. There are infinitely many lines, right? We see that the Q started at that point up there, x f of x. And then as it moves, it has infinitely many points to go through until it reaches point P. But when it reaches point P, well, we can't compute anymore. Because as soon as point Q and point P fuse into a single point, their x values become the same. And their difference is? What's the difference of x coordinates in that case? 0. And can you divide by 0? No, you can't. So algebra will fail in computing the slope of the line. And make no mistake, there is a line there. There is a linear line that goes just through this point. And I'll put that line red because it's special. The red line is called the tangent line. And this tangent line goes through a single point, and in its rightful definition, it's always perpendicular to the curvature, whatever that means. I'll explain. But so tangent line, we actually say kisses the function, right? Because it touches only exactly at one point, right? So you have one mouth, you can kiss one location at one time, right? So that's why we say kisses the function. So tangent line, let's go with so tangent line touches the function. At one point perpendicular to the curvature. Let me explain this perpendicular to the curvature business. The best way to explain this is to use a circle, which is actually not a function, but doesn't matter. So here's a circle, and I have radius r. Now, the tangent line would be there, and you see that there is a 90 degrees angle between the tangent line. Maybe I should draw the tangent line red to be consistent with the... So the tangent line, as you can see, is perpendicular to the radius, and radius is the one that swipes the curvature. We can draw the same situation anywhere on the circle. Now, what is true in mathematics is, let me just draw this tangent line here. Again, as you can see, it's perpendicular. What's true in mathematics is that any curve you draw, it doesn't matter what that curve looks like, there is going to be, for, you know, some amount of that curve, there is going to be, let's say you pick from here to here, right? There is going to be a circle that you can draw, and then it will have the radius, it will have the tangent line, it will have the 90 degrees. So it doesn't matter what type of a curve you have. These circles are going to be small for sharp curves and very large for large curves, right? But the radius always exists. And in some cases, you might just see a curvature and then the line coming in like this, meaning the radius, and then giving you the radius is equal to whatever value, and so on. So you can, this is for your technical drawings especially, right? So curvature is well defined by the circle that fits that curve, and then the radius of that circle will be always perpendicular to the tangent line. So at each point, I have to write this in blood as well, at each point you can only have one tangent line. It's like Highlanders. At each point of f of x, there is exactly one tangent line. And please, tangent line is a linear line, y equal mx plus b. So don't give me answers in x squares and 1 over x's and things like that. So tangent line is linear line. I'll write that as well. With equation. So tangent line is a linear line with equation y equal mx plus b. So it has a slope and it has a y-intercept. It's a linear line. It's a straight line. All right, now I'm going back to the picture from before. I'm going to copy this. You're going to draw a new one, I guess. I need exactly the same picture because we are not done with this. So draw a new picture. And now we are going to talk about the tangent line. All right, so let's take a look at the new idea. So we know that the secant line, which are all the blue ones, m secant, have now the formula of f of x minus f of a divided by x minus a. There are infinitely many of those between any 2 points q that you can pick. And the slopes are well defined through the formula. The issue arises when point Q and point P fuse into a single point. So when point Q gets to point P and they become same point. At that instance, the denominator is 0. And we cannot use algebra to compute the line. What can we use to compute the line at that point? The slope. Well, one of the calculus concepts. Which one would that be? It doesn't care about computation at the point, but it cares about all other locations leading up to it. Limit. See that? It fits. It fits so perfectly. M tangent will simply be the limit of m secant as x goes to a. Do you see that q goes to p because it's moving? Well, that means that at x goes to a. X goes to a. Now write it the way we write it. X goes to a, right? So now, what is this m tangent? M tangent is going to be the limit as x goes to a of f of x minus f of a divided by x minus a. That's what it is. And actually, this is the first definition of the slope of the tangent line, which we are not going to use, but it's the first definition that is that we write. It's the natural one because the limit concept fits so well. And we use it only to compute the slope of the tangent line. As soon as Q passes P, it will continue generating blue lines and m secants, and we can go back to algebra and compute the slopes. It is just at this one point when they collide that we have to use calculus, which is limits, to figure out the slope of the line. And we call it a tangent line. It's a special point. So this is the slope of the tangent line. So now that I have the slope of the tangent line, I can work out some magic here, because I want to create an easy calculation for myself. I want to be able to quickly go through the computation rather than, to solve this, the limit in this form. So what we are going to do is we are going to say, let age be equal to x minus a. And then from here you can solve for x. X is equal to a plus age. And now plug in. Let's see what happens. So now m tangent becomes limit. X is now a plus age that goes to a. It'll be a bit weird, but we can deal with it. The numerator f of x becomes f of a plus age. minus f of a divided by h. In the limit, we are going to subtract a on both sides, and we get the new and improved formula for m tangent. Are you ready? M tangent is equal to the limit, h goes to 0, f of a plus h minus f of a divided by h. Do you recognize the formula? Anyone? Yes, you do. The difference quotient. Difference quotient, the one formula that you were asked to just aimlessly compute in your pre-calculus class and memorize for no reason. Well, it gives you one of the pillars of our civilization, which is the derivative. Guys, all of physics, all of engineering, everything we have, everything that we created as a species is in that box there. It's insane. It's literally insane. Now, it wasn't defined this way in 1600s, but you have to appreciate that only 350 years passed. And we went from banging two rocks to make fire to what we have. We are still very primitive, okay? We are still very primitive in terms of how far our imagination goes and where we could go as a species if we don't blow ourselves up. But for 350 years, to go from, you know, as I said, banging two rocks to make fire to where we are today, I think it's a pretty impressive growth and development. And also, it's really cool to be able to fit something like that in the box, okay, like this. Differential equations course. So differential equations course is the one that gives rise to all of physics and all of engineering and all of everything you do. So that, and differential equations is actually equation that contains the derivative, hence, right, eventually something like this. All right, so now we have to go on and keep pushing and keep developing this. Before we do any other, since everything we did so far was theory, right? We started with the algebra, slope of the line, upgraded slope of the line using pre-calculus, right, notation of the function, realized that secant line becomes a tangent line at the single point when the points collide, gave the definition for the tangent line and explained what it is, and finally wrote down the formula which computes the tangent line. So let's compute the tangent line. So find the tangent line. In the future, I will just put TL. So you know, when I put TL, you know what it is. So when I say find the TL, that's the tangent line. Find the tangent line at x equals 3 for f of x equals x squared minus 2. Well, all I need to do is to compute the limits of the difference quotient. It should not take too long if you know how to deal with the difference quotient. If you don't know how to deal with the difference quotient, well, learn it again, right? Because we did it in pre-calc, we did it as a review on a day one, and clearly you can't move past that point if you don't learn it again. So to create the difference quotient, first off, let me make this clear. A is equal to 3. because it is x equals a. Remember what happens at the picture. X goes to a, and I want to compute at 3, so a is 3 and x goes there, so they're all the same point. X equals a equals 3. Right, so that's something that it's important, because you have to plug that a in, right? It's in the formula. So a is 3. All right, let's go. I need to create f of a. Well, that's easy. That's a squared minus 2, which in our case is 3 squared minus 2, which is 7. Nice. I also need to create f of a plus h. Now that is a little bit trickier, but it can be done. As you can see, my x from f of x is replaced by a plus h. So x is replaced by a plus h, and still squared and minus 2. So all of that stuff works together. And now we expand this, so that's a squared, here's your grade killer term, 2ah plus h squared minus 2. And ultimately, f of a plus h, when we plug in 3 for a, is going to be 3 squared plus 2 times 3 times h plus h squared minus 2. That's 9 minus 2, it's going to be 7, plus 6h plus h squared. So a is 3 in this example. A is 3 in this example. So now what I can do is I can compile the limit finally. So h goes to, limit of h goes to 0. Now, let me write the formula one more time. So it's f of a plus h minus f of a divided by h. And now we plug everything in. So limit h goes to 0. F of a plus h is 7 plus 6h plus h squared. Minus 7, which is f of a, divided by h. As you can see, the 7 dies. And we have limit h goes to 0. Now I can factor h. Gives me 6 plus h in parentheses, divided by h. And now this h dies, which is great. And we have limit h goes to 0 of 6 plus h. And the answer is 6. So what I found is that the m tangent is 6. Find the slope of the tangent line. Well, it's 6. It's right there. But I really didn't want to find that at 3. I wanted to find the slope at -4. So f of x equals 2x squared minus 2. It's the same function. I just wanted to find the tangent line at -4. Oh well, from scratch. Right. So f of a is -4. That's a 16 minus 2 is 14. Okay, and f of a plus h, that's going to be a plus h squared minus 2. That's a squared plus 2ah plus h squared minus 2. Which is what? 16 minus 8h plus h squared minus 2 for a total of 14 minus 8h plus h squared. Perfect. I limit h goes to 0. f of a plus h is 14 minus 8h plus h squared, and then minus 14 for f of a divided by h. 14s will cancel. I can kick out an h, leaving it as negative 8 plus h in parentheses. Then the h that we factored and the h in denominator cancel. And we have limit h goes to 0 of negative 8 plus h. Well, if h goes to 0, then the answer is negative 8, and m tangent is negative 8. It's the same procedure, just we had to go from scratch because we changed. Oh wait, I put x minus 4. I actually wanted x equals negative. Oh. Okay, x equals negative 25, sorry. So f of x is equal to x squared minus 2, but x equals negative 25. That's what the tangent line slope. So what's the slope there? All right, from scratch. And I'm pretty sure that as soon as we're done with negative 25, I will want x equals 7. I can feel it right now, even without getting through this one. I can feel x equals 7 coming up next. Oh well, such is life, right? So f of a is negative 25. Wow, that's squared. That's 625 minus 2. That's 623. And then f of a plus h, when we square that, we get 625 minus 50h plus h squared minus 2 for a total of 623 minus 50h plus h squared. And now we do the limit again. Of h goes to 0. 623 minus 50h plus h squared minus 623 divided by h. 623 will drop. We factor out h with a negative 50 plus h in parentheses. Now these guys drop. And we have the limit h goes to 0 of negative 50 plus h, which gives us negative 50 for the slope of the tangent line to be equal to negative 50. And here it is. I sense it, but yep, f of x is x squared minus 2, and now x equals 7. Can anyone tell me what the answer is without computing? 14. Seems there to be a pattern, right? Because 3 went into 6, negative 4 went into negative 8, negative 25 became negative 50. Well, it seems that each one of these was just doubled, so 14, yeah. Yeah, it was nice because the function was x squared. Generally, it's not that nice. So how do you deal with the multiple requests, right? Multiple slopes need to be found, and every time you have to restart the calculation. Our m tangent right now is defined as the limit h goes to 0 of f of a plus h minus f of a divided by h. I hope you see a's over here. It is the particular number which gets plugged in, and you have to grind from scratch every time you change it. Does it make sense? Because as soon as you change that number, entire calculations change for this and this, right? They are different functions, as you can see. This one had the 14, this one had 623. They're different. Every time I change value for A, all of the calculations change. So you know what? Let me just do this in general terms. Instead of having A, the point, let me put X, a point, right? And then just work through that. So let me rewrite this M tangent as the limit of h goes to 0 of f of x plus h minus f of x divided by h, and put big fat box around that. Because I would like to use this one. You see, now I don't have A anymore. And if I don't have A anymore, well, we are actually computing all of the tangent line slopes. All of them. So now, if I have f of x, x squared minus 2, and someone says, what's the slope at? I say no more. Let me first figure out all of the slopes, and then you can tell me your individual slopes you want to find, and I will use the formula to generate them all. See, now I have f of x. I create f of x plus h, which is, we replace x with x plus h in the formula. We get our standard calculation. And now, no a's. Everything is in terms of x. We plug that in the limit and work out the algebra. So x squared plus 2xh plus h squared minus 2 minus, and in parentheses, original f of x, which is x squared minus 2, everything divided by h. Get rid of the parentheses, and at that stage all of the terms which do not contain h should cancel. If you did everything right, all of the, what I say, non-h terms should be gone. Well, positive x squared, negative 2, positive 2. And as you can see, only the terms with h remain. Factor out h, you are left with 2x plus single h over h. Now h cancels. And we have the limit, h goes to 0 of 2x plus h, which is 2x. You see that when we compute the general formula, you get 2x. So now, what were the inputs from before? We were asked to compute at x equals 3. Well, your slope of the tangent line is 2 times 3, which is 6, and that was our first example. Next example was x minus 4. M tangent for that one was 2 times negative 4, we had negative 8. X equals negative 25 was next. M tangent is 2 times negative 25, we had negative 50. The last one that I was hinting, we didn't do it because you guessed it, 2 times 7 was 14. I do not have to go back and redo the entire procedure because all of the functions change if I change A. Now, I have the function, listen carefully, I have a function that will generate every slope of the tangent line. Let me write that in blood. I'll just write over here 2x. I have a function which will generate every slope of the tangent line. So I have a function which will generate every slope of the tangent line. You need to copy something? Yeah, okay. So I have a function that will generate every single slope of the tangent line, and that function is 2x. What's the name for that function? The name for that function is the derivative. So what is the derivative in a nutshell? It's a function that will generate every slope, every tangent line slope. Why is that important? That slope measures the change. And we will have 2 chapters now to work on it. But as I said, the most important concept, when you say miles per hour, guys, that's a derivative. The instantaneous speed, the one that you pay the ticket for, when you get pulled over, right, that's the derivative. The speed which you are reading as you glance on your speedometer, that's the derivative. And its ratio, it's miles per hour. And we are going to distinguish between the average speed and the instantaneous speed, which is the derivative. The average speed is going to smooth out all of the derivative speeds, because as you drive, I hope you stop for red light and stop signs and things like this, right? Those. So now, over here, slightly different color, I guess. The name of such function is the derivative. So what is the derivative? The derivative is the function which will generate slopes of all tangent lines. Why is that important? Because the tangent lines, the slope of the tangent line is the one that measures change. Now let me draw a picture that will somewhat explain this. If I have a slope, you know what, first let me, no, that's bad. I have to just fix it a little bit. There we go. Much better. I need a flat piece, okay? So this is flat over here. I need a flat piece, and then I need a slope and stuff like that. So now look at this. Let's talk about change of height. In distance. First off, let's understand that if you are not moving forward in distance or time, or both, right, there will be no change in height. Can we understand that? Observe this cell phone. This cell phone is at certain height right now. Let's call this height 6 feet from the floor. And it's just there. Now, if I want to change the height, the time will pass. 1 second. See that? It went up. 1 second. 1 second. down. The change happened in time, and I will denote that later as dy dt. dy, change in height, dt, change in time. Your speed in miles per hour is 60 miles per hour, meaning you go 60 miles forward in 1 hour. That's what 60 miles per hour means. It's a rate of change, right? So we measure change, and any change that you can possibly conceive, I don't care whether it's change of population or change in speed or change in whatever, is the derivative. That's how damn important this thing is. It measures every change that it's known in a galaxy, right? Now, let's take a change of height in distance. As I go, so let me put the distance, so this is your x-axis, and I'll call that distance. Displacement, distance. Now, observe that from x1 to x2, there is no change in height. No change in height. And then from x2 all the way to x3, we are losing height. Observe any or all tangent line slopes. They're all negative. All slopes are negative. Now, it's not just that I want you to observe that all slopes are negative, but I also want you to observe how much negative they are. The more... hold on, let me just get these cables out of my way so I don't die. There we go. The more negative, the steeper the fall. And these less negative slopes are less change in height. So now this means bigger the derivative, more the change, smaller the derivative, less the change, right? So again, calculus is a study of change, and derivative is the chief over there. All right? It measures using the slope of the tangent line. And the slope of the tangent line, guys, you can literally use your, to understand, just use algebra, is change in y over change in x, which means how much do I fall down as I move forward, right? Something you need to know if you play PUBG and dropping, right? You want to go pachinki, I mean, you gotta hit the landing, right? Grass hockey, you want to hit the hill, right? Like anyone playing? No? PUBG? What the hell is this? You guys are so weird. I don't know. We're gonna have to. How many of you play video games every day? I don't care if it's phone games or PC games or 1, 2, 3, 4, 5. What the hell is this? I don't know. Like, how are you in Calc1? I guess you have to hit the alcohol once in a while. My research over 3 years, which is 3 times 4 semesters times... probably pulled more than 30, 40 classes. Always had Calc1 at least 50% of students are playing every day. What the hell is this? Anyway. So now we have the idea of what the derivative is, and we know that it's I don't want to say related to tangent line. It is, right, the tangent line. So what we have now is some kind of a procedure here. We know that the slope of the tangent line is going to measure the derivative. The slope of the tangent line is going to measure the change. The derivative is the function which will generate all of the tangent lines. So we have all of those connected. What we need to do next is to find derivative for any other function than x squared minus 2, right? So let me go into notation mode for a second. So the derivative is denoted by y prime or f of x prime or dy dx or d dx of f of x. So there are many more notation than this. All right, the Newton's original notation was y with a dot on top, and only mechanical engineers might use this. If you have a professor who's teaching, any kind of mechanical engineering course at the 4-year school, and the professor is more than 130 years old, probably will be using this. I've seen it before, and it's really good. Other notations would be capital D of something in here, function, will be used in linear algebra. Also, you will have partial derivatives, which will have this type of notation in Calculus 3. That's coming up, and that's all equivalent to what we are doing. Now, major notations for us, and about 90% of the time, 95% of the time, I will be using this one because it is the best. Combined with this, obviously, but that's pretty much the same. You know that f of x is y, and then you just put it there, right? So it's not a big deal. So 99% of the time was going to be this, and then that 1% of the time is going to be that. And this I might write twice in the entire course, once being right now, because I'm going to finally say that the derivative is given as the limit h goes to 0 of f of x plus h minus f of x divided by h. I'll put this one on a cloud. Okay. That's the derivative. I want to use this on functions that are different than polynomials. So let's go and figure out this thing for, let's say, f of x, the square root of x. Now, as you can see, these problems now become 2.3 problems, right? From your chapter on limits. Because if you know, and you should know, how to set up your difference quotient, the rest is actually working out the limit procedure, which is outlined in 2.3. So on your exam, which is coming up at some point, Thursday, this week, this year, yep. The question will say, find the limit. I could say find the derivative. There's no difference between the two, right? Because finding the derivative, you find the limit. That's all it is, right? I mean, finding the limit finds the derivative, because that's what this definition is for. So, pardon me if I use the wrong word. I should not use the word derivative on the first exam, but here I am saying that, hey, that's 2.3 calculation. Let's do it now. I need f of x plus h piece, which is simply replace x with x plus h. So there it is. Now I need to compile. I'll put f prime of x equals. Oh, this is the second time I wrote it, so that's it. I used it up for the course. Limit. Yeah, watch me forget that next class. Someone should remind me. So limit h goes to 0. I have f of x plus h, which is square root of x plus h, minus root x divided by h. 2.3, take it away, right? That's all it is. So what should I do? How do I solve this? Anyone? It starts with rationalize. It's the only thing you can do. Root x plus h plus root x divided by root x plus h plus root x. So this is now limit h goes to 0. In the numerator you have difference of squares, so the midterms will cancel. So we have x plus h minus x. Right? The cross terms cancel. And on the bottom, I'm not going to multiply. I'm going to leave it as is because I have experience with these things. You will discover as you go along, which, I mean, technically you never multiply and FOIL in the denominator. So now in the numerator, as you can see, x's will drop, and you have h divided by h times the parenthesis. Do you see now that the h drops? All right, so now 1 over square root of x plus h plus root x. What do we have? As h goes to 0, you have 1 over root x plus root x. And how much is that? Apple plus apple is 2 apples. Very good. Done deal. Apple plus apple is 2 apples. So now I know that the derivative is 1 over 2 root x. What is the slope of the tangent line at 9? Very good. All right, if x is equal to 9, then it's 1 over 6, right, for the slope. So, maybe not put this line. So, m tangent equals question mark at x equals to 9. What I have is f prime of 9, which is 1 over 2 root 9, which is 1 over 6. If you take a look at the graph of the square root function, this is 9. The tangent line is right there, and the slope is 1 over 6 for that line. It's a sluggish slope because the function is not rising very quickly. So 1 over 6, it's a sluggish slope. All right, here's one for you to enjoy. Say f of x is 1 over 2x. We want to find the derivative. And then later compute the slope for x equals to, let's say, 5.
Hmm? F of x is supposed to be 1 to square root of x versus 2x.
Why square root? It's just a function. This is a new problem. It has nothing to do with the previous problem. This is the new function, a new calculation. All right, let's take a look. So I already set it up, if that helps in any way. When you have these fractions, the only thing you can do is to add them, I mean subtract them in this way. So it will be the common denominator between these fractions. So I have limit h goes to 0, and then we are going to, well, denominator is h. Then we're going to cross multiply. The common denominator is 2 x plus h times x, right? So we have x minus h in the numerator. I'm not multiplying the 2 because 2 is common already, so there's no reason to multiply 2. Okay, so now x's drop, and you are left with the negative h in the numerator. So limit h goes to 0. We can write over 1 and then do the double fraction. So 1 times negative h is negative h, and in denominator we have 2xh x plus h. So 2 that are far apart multiply, and 2 that are close by multiply for the double fraction, if you remember a over b over c over d. So now when I have this, h will drop, and I will have limit h goes to 0 of negative 1 divided by 2x x plus h. Now when h goes to 0, because h goes to 0 in the limit, we are left with negative 1 over 2x squared. And that is actually our derivative. F prime of x is negative 1 over 2x squared. Now we wanted to compute this at 5. Not a problem. Slope of the tangent line is going to be computed at 5 in this case, so that's negative 1 over 2, 5 squared, which is negative 1 over 50. So the slope of the tangent line is negative 1 over 50. Again, if we switch x out, we only need to compute the last calculation. We don't have to go back because the derivative gives us the function which generates all slopes. Maybe I should write it here. F prime of x equals 2, and there we go. So we got the derivative, and then we can generate any slope we want using that derivative. Now, to find the tangent line, we need to compute b, right? Because we have y equal mx plus b. We already computed m, it's negative 1 over 50. We need to compute b, which is the y-intercept. And you can simply do that using algebra. We are not developing any calculus way to compute b, because computing b should be very easy and straightforward. You have a point, you have a slope, calculate b, and you're done. So for our example before, what do I have? I have f equals 1 over 2x. I have that x is equal to 5, and I have that the m tangent is negative 1 over 50. Well, I should be able to compute b from here easily. First, I need the y value, right? So the y value is f computed at 5, which is 1 over 10. So the point is 5, 1 over 10, and the slope is negative 1 over 50. Not 15, 50. There we go. So all I need to do is to plug everything into y equal mx plus b, or you can use the y minus y1 equal x, m times x minus x1 if you want, whatever, it doesn't matter. Or y minus y1 is equal to mx minus x1. So whatever formula you want to use. I'll use both, obviously, to show, but then you pick one. I generally always use the one on the left, but, well. So I have y, which is 1 over 10. I have m, which is negative 1 over 50. I have x to be 5, and I have this, why I put negative b? It's plus b. There we go. So now these will cancel into a 10. So now this adds to 2/10 is equal to b, so b is equal to 1/5. So slope is y equals negative 1 over 50x plus 1 over 5. So that would be the tangent line. Or on the other side, we have y minus y1, which is 1 over 10, is equal to negative 1 over 50 x minus 5. And now you compute this, which will give you the same. So y minus 1 over 10 is equal to negative x over 50 plus 1 over 10. Y equals negative x over 50 plus 2 over 10. And y equals negative x over 50 plus 1/5. And that's that. So one or the other, not both, whatever you are more comfortable with. They're both studied in algebra, right? So you should know both of these procedures, but then again, just pick one and be the master of that one. In your case, PhD of that one. Sounds good? Perfect. That ends our introduction to derivative. I hope you're not disappointed, but that's it. So we start in algebra with the basic slope, through pre-calculus, turn it into the one with functions, and then we find the slope of the tangent line using the limit, and then we go to the next step of figuring out every point, right, which gives us the derivative. And now all you have to do is to practice 2.3 calculations to get this type of calculation. That's 2.3. We are adding the concept of the derivative as new. And then to find the tangent line, all we need to do is to find b in addition to the slope that you already have. And you have the tangent line at the end. And that's 3.1. So, bye.